Let's talk about the nomenclature of molecules that have multiple priority groups in systematic nomenclature. And so our outline never changes. We're always going to first circle the parent chain. We're then going to label the groups that intersect that circle. We're going to number the parent chain, and then we're going to put the name together, thinking about stereochemistry, putting that at the beginning of the name. So those four things never change. What changes are the way we pick the parent chain and number the chain. And so when you pick the parent chain with multiple priority groups, there's a lot of things you have to think about as far as tiebreakers go when you're picking this parent chain. And so our first thing, we do all of these rules in this order, is that we select the parent chain that contains the greatest number of the highest priority group. Okay, so if you've got the highest priority group, you might have one, you might have two. That chain's going to have the highest, as many of those priority groups as you can. And the highest one, okay, so it must be the highest priority group is your only concern at this point. If you can get one either way or two either way, you then pick the maximum number of double bonds or triple bonds in the chain. And if there's a tie between double and triple, you pick the one with the most double bonds. They win the priority because doubles slightly or is greater than triple bond when there's a tie. Notice the third thing you apply is the longest chain, the greatest number of carbons in the chain. Okay, so we don't even talk about the greatest number of carbons until rule number 3. So your first priority in picking the parent chain, and this is a rule that many textbooks get wrong, naming software gets wrong, you've got to pick the most priority groups first in the chain, the maximum number of double or triple bonds next if there's a tie, and then if that's a tie, you then pick the greatest number of carbons in the chain. Okay, so that is something you have to do. Okay, and maximum number of double bonds actually, comes right after greatest number of carbons. So if there was a tie between double and triple, the greatest number of carbons wins, then the greatest number of double bonds wins. Okay, after that. Okay, if the number of carbons are the same. So then we go by our old school rules. We lower the number of the priority group if we're tied still. We lower the double bond or triple bond that we see. So the first double or triple that we see in the chain. And then if tied, we pick the most branched chain. So this is the same as alkane nomenclature. The more branches, the greatest number of substituents, whether they be carbon branches, chlorines, amino groups, whatever. Most branched chain is the parent if all these are tied. And then if that's still a tie, lowest number to the first substituent. Okay, if that's still a tie, after all the substituents have been exhausted, okay, so the first substituent, then the next substituent, and so forth. If that happens, we're going to pick the lowest first substituent encountered that's alphabetically lower. Okay, and if all that ties, you've got a symmetrical chain, and it really doesn't matter which way you pick the parent chain. Okay, if everything ties, you've got the exact same chain no matter what you pick. So the best way to exercise these rules, these sequentially applied rules, is to do examples. But first, let's take a look at numbering the chain and then our order of rankings for the priority groups. So when we number the chain, the lowest number always goes to the highest priority group. Okay, so that's something we see. And if there's a tie, we number by lowering the alkene or alkyne. And if that's tied, or there are no alkenes or alkynes, we're going to lower the number of the first group encountered. And then if tied still, the next group needs to be lowered. And then finally, we lower the first group alphabetically if there's still a tie. Okay, so the old rules come back for numbering the chain as well. Putting the name together, so this is a lot of priority groups, so let's have a look at all of them at once. Okay, we start knowing that the end of our molecule is going to end in ene-ine, because these are special groups. over here, the alkene and alkyne are special because they're included in the parent chain. So they are actually a part of the carbon-to-carbon chain and not intersecting the circle you draw around the parent chain. And so they get positions at the end of the name, ene, ein, and then any of these groups that appear, we add the suffix that you see that I've highlighted yellow. So it might be ene, ein, ol, or ene, ein, amine, and so forth. Okay, so one of those things, ene, ein, al, would go, ene, ein, nitrile, ene, ein, oic acid. Okay, and so we'll see how those names go together here with the examples we're going to see. And if anything appears to the left of a priority group on this list, the priority group gets subjugated to its group name. So if there's an OH present and an NH2, the NH2 group on the parent chain becomes an amino group. It gets subjugated to the highest priority group. At that point, becomes an ordinary group as far as nomenclature is concerned. So we've talked about the theory of it. Let's do the examples and see how we apply these. And so rule number one, pick the parent chain that has the highest priority group. So amine is the furthest to the right, okay, or the furthest to the left in the chain, and so it is the highest priority group on this particular IUPAC, this particular organic molecule. And the next rule is maximize the number of double or triple bonds. The third rule is maximize the number of carbons. So we pick a shorter parent chain that has the double bond in it because we never actually get to the rule where you pick the longer chain. Lower the number of the highest priority group in numbering. And so this is going to be an amine suffix here. And this is a 1, 2, 3, 4. This is a butyl group. And so stereochemistry wise, okay, didn't show a chiral center here. Why not show one? Make that a wedge right there, okay? And so at the amine position, this is group 1, and then 2, and then 3. It looks like it's counterclockwise S, but because H is coming at us, it's actually R. And then here we have double bond beats single carbon to 2 H's. And so then single carbon to 2 H's with a nitrogen wins. So there's a 1, a 2, a 3, and then 4 is back. So this one is a true R right here. It's clockwise rotation. And the double bond has no stereochemistry, so putting the name together here, we're going to have out front stereochemistry 2R, 4R. We have a hex 5 ene ein ol, 5 ene, no ein, so it drops out, ene ein amine, 2 amine, hex 5 ene, 2 amine. Don't forget our group here. Anything intersecting the circle gets a locant, so this is a 4 butyl, hex 5 ene, 2 amine. 2R, 4R, 4 butyl, hex 5 ene, 2 amine. Next example. Parent chain is a ring. Highest priority group is ol. Anything appearing to the left of amine means it becomes subjugated to an amino group. So it gets a prefix rather than a suffix. And this is an ene. Our numbering rule, lower the number of the highest priority group and then lower the number of alkene. So we've got a 1, 2, 3, 4, 5, 6. Okay, the amino group loses its priority because alcohol group is higher priority. Okay, so we've got a little bit of stereochemistry to take care of. We've got carbon to 2 carbons, carbon to a nitrogen, oxygen wins, then to nitrogen, and then carbon to carbon. That is a counterclockwise. 4 is back, so that's an S. Here the amino group wins. There's a 1, a 2, a 3. That's a R, a clockwise rotation, but H is coming at us, not away, so it becomes an S there. Okay, putting the name together, we have a 1 parentheses 1S 6S 6 amino, cyclo because it's a ring, hex because there's 6 carbons, cyclohex, ene amine or ene ol here, hex 2 ene, no ine, and then we don't need a 1 because the highest priority group automatically gets a 1 in a ring. It doesn't matter where that priority group is on the ring, it automatically gets the 1 position. It's just a 1s, 6s, 6 amino, cyclohex 2 enol. Okay, then finally here, parent chain is not up for debate, but we're going to put our nomenclature to the test here. Lower the parent, this is an ol, lower the highest priority group. There is stereochemistry here, that's a Z, because you've got high, low on the same side. Highs are on the same side, lows are on the same side, so that's a Z isomer. No stereochemistry for a triple bond. There is stereochemistry here, 1, 2, 3. That's counterclockwise, 4 is back, so that's an S. Okay, so putting this together, we're going to have to use our full ene ol here, but this is an S, don't need the number because there's only one chiral center. This is an S. Oct ene ol, oct 6 ene 4 ine, drop the E if there's something to the right, 2 ol, forgot my EZ stereochemistry here, so in order of appearance, carbon 2 has the S, carbon 6 has the Z, so it goes in that order, SZ, not ZS. SZ, oct 6 ene 4 ine 2 ol. You could also write this one and all the others with the non-split convention, which would bring out the first group that appears, 6 octene 4 ine 2 ol, as an example of how you would incorporate the first priority group at the end. You incorporate that into the parent name and it's equivalent. The two methods are the same. And if you wish, we can go back and name the others in the same way using that split convention. And so we'd have a 2R, 4R, doesn't change. 4-butyl doesn't change. But then you bring the 5 out front, 5-hexene, 2-amine. Okay? And then for the other example, the middle example, we'd still have 1S, 6S, 6 amino, 2 cyclohex enol.